Hi there, this is MG5004 DE5418, Topic 12, Class 1, and we're now looking at differential equations. And many of engineering models are couched in terms of how changes in, say, A produce proportionate changes in B with some constant of proportionality. There are several worked examples in the textbook. There's an example 1.4 where it's looking at chemical engineering, and there's a tank of liquid, and the liquid can flow out of the tank through a valve at the base, and as it does so, obviously the height of the liquid or the head of the liquid in the tank will change, and obviously the volume of the liquid in there will change. Another example is the vertical motion of a projectile. So when something like a ball is travelling vertically under the action of gravity, we would describe its motion by a differential equation. In mechanical engineering, bending moments, you talk about Young's modulus and the moment of inertia. All of that is modelled in terms of what we call differential equations. So it's related to integration, it's kind of related to differentiation as well, but it's to describe situations where there's more than one thing potentially changing. In these examples you can see what I mean. There's a right-org mix of x, the derivative of y with respect to x and y, and it's all muddled up together. I suspect that's actually supposed to be a plus in there. And the second one, there's a second derivative that's multiplied by x and y, and that's added to y times the first derivative, plus a logarithmic function, an exponential function as well. So there's relationships there between x, which is the independent variable, y, which is the dependent variable, and one or more derivatives of y with respect to x. You already know what an equation is. An equation is just something where it contains this idea of an unknown quantity, and if you're solving an equation, then you're looking to find that unknown quantity. A differential equation is kind of the same. It's an equation, but this time it contains the derivative of an unknown expression. In this equation, dy by dx equals x squared, there's the derivative of y, which represents the unknown expression that we're looking for. Clearly, y is an expression that when it differentiates, it gives x squared. In order to solve a differential equation, we need to identify certain features. This is because there's so many different techniques applicable to different types of differential equations, so we need to know the type that we're dealing with, so then we can choose the appropriate technique. Firstly, it's a matter of deciding which is the independent variable and which is the dependent variable. So in the first example there, as it notes that x is the independent variable and y is the dependent variable, those are, that's the standard stuff that you've had way before. The second one, t is the independent variable and x is actually the dependent variable. So it's a little bit different now that we've got the derivative, because we need to look, it's the derivative of x with respect to t. So x is actually dependent on the value that you've chosen for t. Let's have a look at deciding here which are the dependent and which are the independent. As a general rule, the dependent variable is the one that's being differentiated. So in the first example here, x is the independent and y is the dependent. In the second one, again, the dependent variable is y and the independent is x. But if you look at the third example there, the dependent variable is x and the independent is t. In the fourth example there, the dependent variable is the one that's called VC, and the independent variable is t. So if we just remember this, we won't go too far wrong. We need to know the order of a differential equation, and the order is the order of its highest derivatives. Now, it's not the power. It's not the power of the derivative. It's which derivative. So if we look at the first one there, the highest derivative is the second derivative. So this equation is of order 2. We would say that it is a second order derivative. The one that's labelled A, now it's got a cubic power. We're not talking about the power. We're looking at which particular derivative is the highest. The highest derivative there is the second derivative. So again, it's a second order derivative. And the third one, it's only got the first derivative, so it's of order 1. We also need to be able to say whether the equation, the differential equation, is linear, and it's linear if the dependent variable and its derivatives occur to the first power, to only the first power, and if there are no products involving the dependent variable and its derivatives. So a point to remember, or a point to think about, is that there should be no nonlinear functions of dependent variables such as sine and exponential functions as well. And here's a really clever statement: a differential equation that's not linear is said to be non-linear. So the linearity, though, is not determined or affected by the presence of any non-linear terms. So let's look at classifying these. The first one is linear. The second one over here has got a power of 2 for the derivative, so it's non-linear. The third one is non-linear because there's a product of the dependent and the derivative. Next one is non-linear because there's a non-linear function of the dependent variable. The next one is linear because this one's e to the y and this one's e to the x, so this one is linear. Now let's look at A. It fits being linear. B is non-linear because it's got a product of y, something to do with y, and its derivative. And that the sign bit, the sign of y, is also non-linear. The part C there is non-linear because it's got the second derivative, non-linear. D is back to being linear again. And E is, it's got that sign of the dependent variable, so it is non-linear. Now, if we have a linear differential equation, we can talk about it having constant coefficients if the coefficients of the dependent variable and any of its derivatives are constant. So 5 is a constant, 3 is a constant, and 8 is a constant. So this is we call this a constant coefficient linear equation. But compare that with the next one. This is not a constant coefficient linear equation. Because the coefficient of the second derivative is x, so it's not a constant. So that's what makes the difference there. The first one, all the coefficients are constants. The second one, the second derivative has a constant of x. Sorry, has a coefficient of x. An example here for the electrical engineers amongst you, that we can model an LCR circuit using a constant coefficient differential equations, because L is a constant, R is a constant, and that is a constant as well. The same logic actually applies to partial derivatives, but partial derivatives we cover a lot more in Eng Maths 2 for the degree. Now we start to get really picky. If we're going to write a linear equation, then all the terms containing the dependent variable are on the left-hand side of the equal sign, and those that involve the independent variable have got to be on the right-hand side, and the constant terms are on the right-hand side. And if we arrange it this way, then we talk about the equation being homogeneous if the right-hand side is 0. And would you believe if the right-hand side is non-zero, then the equation is said to be non-homogeneous. Now, we need to start looking at how we're going to solve these differential equations, and the first way is just by directly integrating. So if we have dy by dx equals some function of x, then clearly y is going to be the integral of that function of x. Here in the video I will do numbers 1 and 3, and we'll do numbers 2 and 4 in class. Let's start obviously with number 1. First up, if we rearrange what we've got, so that we can rearrange it so that dy by dx is equal to 2 minus 4x cubed over x. Now, we can't deal with it as it looks like that, but if we rewrite it like that, then we're ready to go. So now we've got the y terms on one side and the x terms on the other side. Now, integrating both sides, if we integrate the left-hand side, we get y. If we integrate the right-hand side, the integral of 2 over x is 2 natural log of x, and the integral of 4x squared is negative 4x squared would be negative 4x cubed over 3, plus, don't forget, the integrating constant. So that would be the general solution there. Looking at number 3, the first step would be to shift the 2t over to the other side. So this is number 3. So we'd have t minus d theta by dt equals 5 divided by 2t. And then we could shift the t and the negative sign. So now we have t minus 5 over 2t. And again, we've got the theta's on one side and the t's on the other side. So integrating both sides, integrating the left-hand side gives us theta. Integrating t, just do a basic step in between. So the integral of t is going to be t squared over 2. The integral of 5 over 2t would be 5 over 2 natural log of t plus c. But in this particular case, we're given that theta is equal to 2 when t is equal to 1. So 2 equals 1 squared over 2 minus 5 over 2 natural log of 1 plus c, and that allows us to work out that c must be 3 over 2. So we can pop that back in here, and then we can write that theta is equal to t squared over 2 minus 5 over 2 natural log of t plus c, which we've now found to be 3 over 2. Take a look at this. This is slightly different. This is where we have an example where the derivative is equal to some function of y. So we could initially rearrange it so that we've got dx equals dy divided by this function of y, and then we could find that the integral of dx is equal to the integral of the right hand side. For example, we might have something like dy by dx equals 3 plus 2y. Now at this level it's not right to mix derivatives, because if we just integrated directly, we'd say that y was equal to the integral of 3 plus 2y dx, like that. And that's a bit tricky at this level. So what we need to do is we need to rearrange and perhaps then think that we might end up with a function that says that x is some function of y. I'll do the first problem in class, but we can look at the second problem here. We have y squared minus 1 times dy by dx equals 3y. So let's initially rearrange it to say that dx is equal to y squared minus 1 over 3y dy. So we've got the x's on one side and the y's on the other side. Now that's looking a little bit tricky, so maybe we can just do some basic simplification. So we've got y over 3 minus 1 over 3y, and all of that is by dy. Now if we integrate the left hand side, we can integrate the right hand side. Integrating the left hand side gives us that x is equal to, now the derivative of y over 3, sorry, the integral of y over 3 would be y squared over 6 minus the integral of 1 over 3y, which would be a third of natural log of y plus c. That gives us the general solution, but we've got a bit more information this time. We've given that y equals 1 when x equals 2 and a sixth. So let's just write that down. When y equals 1, x equals 2 and 1/6. So putting that in there, we can find c. So 2 and a sixth is equal to 1 squared over 6 minus 1 over 3 natural log 1. So c is equal to 2. So putting that in, we're going to get the particular solution that x is equal to y squared over 6 minus 1 over 3 natural log of y plus 2. So this is the particular solution. An example now, a practical example, a real life example, where you're given that dr by d theta is equal to alpha r, and alpha is the temperature coefficient of this particular case. It's of aluminium because it's an aluminium conductor. Okay, let's rearrange that so that we've got d theta is equal to dr divided by alpha r. Then if we integrate both sides, and bearing in mind that alpha is a constant, so then the left hand side becomes theta and the right hand side becomes 1 over alpha because it's a constant, and it's constant on the bottom, and r is also on the bottom, so natural log of r plus c. So that's our general solution. Now we're given some conditions. We're given that r equals r naught when theta is 0. So we can put those in. So we can say then that 0 equals 1 over alpha natural log r naught plus c. So that gives us that c is equal to negative 1 over alpha natural log r naught. So we can put all that together now. So theta is equal to 1 over alpha natural log of r minus 1 over alpha natural log of r naught, which we could take out a common factor of 1 over alpha. And what do we know? We know about the rules of logs that will allow us to write that theta equals 1 over alpha natural log. It's a division sum. Or we could write alpha times theta equals natural log r over r naught. Now that's probably not how you've seen it in textbooks. What we can do is to get rid of the natural log, and then it will look a bit more like you will see it in textbooks. If we take each side to the power of an e, so then we say e to the power of alpha theta equals r over r theta. Then if we rearrange that, we'll get something you know and love that says that r equals r0 e to the alpha theta, which is a standard formula. Now for part B, all it is substituting all in the numbers that you've got to find the resistance at 50 degrees. So if you put all the bits and pieces in, then you would have the resistance at 50 degrees is 24 times e to the power of 38 times 10 to the negative 4 times 50, which is approximately 29.02. Oops, that won't draw. Try that again. Ohms. A second way of doing it is called separating the variables. So we try to rearrange it so that all the terms with the dependent variable are on the one side and all the terms involving the independent variable are on the other side, and then it's a matter of integrating to find the solution. Not always possible, but sometimes it works. If we have a differential equation where you've got dy by dx is equal to some function of x times some function of y, then we can rearrange that so that we get the y terms on the left and the x terms on the right, and then we can integrate. Let's have a look at the first one, and the second one we'll do in class. Okay, so we have 4xy dy by dx equals y squared minus 1. So if we rearrange that, we can get 4y divided by y squared minus 1 dy is equal to 1 over x dx. The left-hand side, let's deal with the left-hand side. We're going to have to integrate by substitution, so let's do let u equal y squared minus 1. So then we're integrating 4y over u dy, and we better find from here, we better find that du by dy is equal to 2y. So dy is going to be du, oops, it's dy, du over 2y. So now we can further rewrite this. This is just the left-hand side as 4y over u times du over 2y. That's not writing y's very well, that's a y. And of course then the y's cancel, and we've got 4 over 2, which we can take out the front, and then we've got, so the left hand side now integrates to being 2 natural log u, which we can rewrite as 2 natural log of whatever u was, which is y squared minus 1. So that's the left hand side. Now the right hand side is a whole lot easier to do, so now let's put it together. We've got that 2 natural log y squared minus 1 is going to equal, now we've got 1 over x, so the integral of that is natural log x plus some constant. Or we could jiggle it around a little bit. We could say natural log y squared minus 1 squared minus natural log x is equal to c. And using the rules of logs, we could say that the left-hand side becomes y squared minus 1 squared over x, and that's equal to c. And further, then we could say, if we raise it to the power of e, we could say that y squared minus 1 squared over x equals e to the power of some constant, and that would be the general solution. And given that we've got no more information, we would leave it there. That would be the general solution. and as I said, I will do question 2 in class. I should be able to have enough space here to do numbers 1, 2 and 4, and to do 3 and 5 in class. Let's have a look at number 1. Now number 1 we can rearrange so that we've got 1 over 3y dy by dx is equal to e to the power of x, and we could integrate just straight off. We could say that the left-hand side, the integral of the left-hand side, with respect to x is equal to the integral of e to the x dx. And what we've got here is, it's a format, I'll write it down here, it's of the form of the integral of 1 over some function of y dy is equal to the integral of some function of x dx, because of course that's just going to cancel that out there. Or we could have done it straight from shifting this onto there. So now we've got the integral of 1 over 3y dy is equal to the integral of e to the x dx. Left hand side, that would be a third natural log y is equal to the integral of e to the x is e to the x and plus c, and we're not given any more information there, so that would be the general solution for that particular differential equation. Let's have a look at number 2. Number 2 we can rearrange so that we've got y, this is number 2, so that we've got y dy is equal to 3x squared dx. So now we can integrate each side so that the integral of y dy equals the integral of 3x squared dx. Left hand side, the integral of y would be y squared over 2 is equal to x cubed plus c. And again, we don't know anything more, so we can't find c. What we could do is we could rearrange it and say that y is equal to plus or minus the square root of 2x cubed plus now some other constant, where, because we've multiplied both sides by 2, where d is equal to 2c. Really neither here nor there as to how we leave it. Let's have a look at number 4. Number 4, we can rearrange so that we've got v dv is equal to negative k squared x dx. Now taking the integral of each side, is equal to the, now negative k, therefore negative k squared is a constant, so we can put that outside. And the integral of v is v squared over 2, and negative k squared stays, and the integral of x is x squared over 2 plus some constant. And again, we don't know enough to be able to find c.